Here is yet another formula for the area of a triangle, but this one's pretty cool, I promise you. It's the following. The area of a triangle is given by the product of r times s, where r is the inradius, which is just the radius of the circle that can be inscribed in the triangle, which is called the incircle, and s is just the semiperimeter of the triangle. It's just half of the perimeter of the triangle. So let's go ahead and look at this diagram on the screen. Here we have the incircle of a triangle with its incenter and its inradius. And what we're going to do is we're going to first draw in these three radii. And notice these three radii will be perpendicular to their respective sides of the triangle. How do we know that? Well, because all three sides of the triangle will be tangent to the circle. And if you remember from your geometry days, anytime a radius of a circle is drawn to a point of tangency, that radius will be perpendicular to that tangent line. Next, we're going to draw in these three segments. These three segments will extend from the incenter, the center of that incircle, to each of the three vertices of the triangle. And notice in doing so, we have now divided the larger triangle into three smaller triangles. So now we can find the area of the larger triangle by simply adding up the areas of these three smaller triangles. And if you think about it, we can actually find the areas of these three smaller triangles quite easily using the standard half base times height formula for the area of the triangle. So doing so, we have 1/2 a times r, 1/2 b times r, and 1/2 c times r, where again, r is the inradius, the radius of the inscribed circle. Adding them all up, we get the following expression, and simplifying, we get 1/2 of r times the quantity of a plus b plus c. But this just all simplifies down to r times s, the semiperimeter, because 1/2 times the quantity of a plus b plus c is precisely the semiperimeter of the triangle. And that concludes the proof, but notice we actually get some bonus facts here. For example, we can solve for r here to get r equals to the area over the semiperimeter. But in addition to this, if we set this area formula, r times s, equal to the one given by Heron's formula, we get the following. Solving this equation for r, we can now get another expression for the inradius. R equals to the square root of s minus a times s minus b times s minus c, all over s. Nice. I always love free stuff. And moreover, I just think it's so cool that we have this intimate connection between two shapes that couldn't be more different from each other. A triangle, which is the simplest polygon, at least in the Euclidean plane, and a circle, which is in some sense an infinite-sided polygon. In any case, you can now add this formula to your arsenal of area formulas for a triangle. With that, I hope you're doing well. Make sure to hit that follow button for more math content. And as always, I'll catch you on the next one. Take care.